So for today's lesson, we'll be going through two other quantities under electric field, namely electric potential energy and electric potential. Okay. Now, before I go to that, let's just recap a little on what you guys would have learned last time from gravitational field. When you guys were talking about gravitational potential energy, GPE, you would have said that in AS last time, that GPE is actually energy possessed by a mass in a gravitational field. This one is your definition that you guys would have used in AS. But then after that, when you guys went on to A2, the definition changed a little, where you say that this time GPE is work done to bring a mass from infinity to a point in the gravitational field. Okay, this was your definition that you guys would have learned in A2 last time. All right, this is probably the first or second chapter that you guys did when you guys started your A2, right? So now when you go on to electric field, you also have something called electric potential energy, and their definitions are actually very similar to that of GPE. So you look at the definition for AS. If you were asked to define what is EPE in AS, EPE would really just be the energy possessed by a charge in an electric field. You really just change out charge to mass, gravitational field to electric field. That's all. Okay, this one would be how you would have defined electric potential energy in AS. But now when you move on to A2, EPE is the work done to bring a charge from infinity to a point inside the electric field. Again, you see the similarity in the definition. You're really just changing mass to charge and then gravitational field to electric field. Okay, so why is it that we specifically say that EPE in A2 is the work done to bring a charge from infinity to a point in the gravitational field? You consider this. Now, electric force always acts on any charge that is situated inside an electric field. Okay, so in our case, if that charge is moved over a certain distance due to the force or against this force, work is being done. You guys remember the definition of work? Work done is actually force times distance moved in the direction of the force. You must have a force and a distance moved in order to have work done. So in our case, for an electric charge that is inside an electric field, if there's a force acting on it and it moves, there is work done. Okay, so the work that you do now is actually equal to the change in electric potential energy of the charge, because you would have learned in your AS work energy power also that work done, work done is actually equal to energy change. Whatever work you do is used to change the energy of that particular object. Okay, so now you consider this. If you're talking about a charge at an infinite distance, all right, so let's just say right now, I give you this particular case. You have one positive main charge here, and then you have one test charge. You place it at an infinite distance from the charge. For the test charge that is at the infinite distance, its electric potential energy is actually defined as 0. The reason for that is because at an infinite distance, you actually have no electric force, so you have no capacity to do work. Again, it kind of ties up to the equation that I wrote on the right-hand side here. If say your force is 0, your work would be 0 too. Okay, so at infinite distance, your electric potential energy is 0 because there's no electric force. Why do I say that the electric force is 0? Is because of what you learned before. If you recall, the electric force is actually 1 over 4 pi epsilon naught QQ over R square. Fe is actually inversely proportional to your separation square. So if say your R is infinite, your Fe obviously would be 0. Okay, so that's why here we will say that your electric force is actually 0. So therefore you actually have no capacity to do work. So right over at this particular point here, your electric potential energy is considered to be 0. Okay, your electric potential energy here is written with symbol W. Okay, don't confuse it with weight, don't confuse it with work. Okay, the W here is really electric potential energy. That's how they define it. Okay, so at infinity, your electric potential energy is 0. What happens if you now try to move this charge from infinity to some random point inside your electric field? You move it from infinity all the way to here, which is a distance r from your main charge. Okay, so let's consider this. If you're talking about the interaction between the test charge as well as your main charge, both charges are actually positive, so they actually experience repulsion. So for the positive test charge itself, it by right should experience a force that is directed towards the right. And let's just consider it as having electric force that's directed towards the right. But your motion is in this direction. The direction of your motion is towards the left. Okay, so you have an electric force that's trying to oppose your motion towards the left. Okay, so this would mean that if you want to move towards the left against this repulsion, you actually have to do against it. Okay, so your positive test charge is moved against a repulsive force, so work is done on the charge. Okay, because you're trying to overcome the repulsive force, you are doing work against the repulsive force, so you are actually doing work on the charge now. Okay, so when you do work on the charge, we will say that your charge actually gains electric potential energy. Okay, yeah, I think I didn't mention this. The positive test charge is always positive. All right, whenever you are trying to test something inside an electric field, your test charge would always be positive. We never use negative charge. Okay, so back to what I was saying, you move a positive test charge against the repulsive force. What is done on the charge? It gains electric potential energy. Okay, so now you consider this. If your electric potential energy is 0, and then you move towards the left, we mentioned that work is done on the charge. Therefore, EPE increases. What would be the value of EPE here? You are actually having your EPE increasing from 0. So whatever EPE you have here would obviously be positive. Okay, so your EPE is going to be positive for any point that's less than infinity. Okay, and also another thing I should mention to you here is that because at infinity, this is your starting point, this is your reference point, where the energy is considered to be 0. So you go from here all the way to here, whatever work that you do is actually equals to the change in electric potential energy. So your change in electric potential energy would be the potential energy at this point itself. That's why we would say that electric potential energy is the work done to bring a charge from infinity to a point in the electric field. You start off at infinity where the electric potential energy is 0. So when you bring it to a point inside the electric field, you do work. Whatever work you do, when to changing the electric potential energy, the change that you have would be equal to the potential energy at that point itself. Okay, that's why we define it as this. Okay, now your electric potential energy here would be positive. There are also cases where your electric potential energy could be negative. This is for electric potential energy, it can have both positive and negative values. All right, so I think I should mention this here. If you refer back to GPE in A2 that time, I told you that GPE is always negative. And the equation would be U equals to negative GMM over R. So the negative here is supposed to reflect this, okay? But when it comes to electric potential energy, you can have positive EPE, but also negative EPE. It depends on the main charge, the sign of the main charge. So say for example, right now I change the main charge to a negative charge like this. Right now, this one now below here is your negative charge. Again, I consider bringing a positive test charge from infinity to a point inside the electric field. As before, at infinity, your electric potential energy is 0. So you try to bring your charge from infinity all the way to here, okay? Now, you consider what are the forces that act on the test charge right now. Because this is positive, but this is negative, you are going to have attractive forces. So the electric force that acts on your charge right now would actually be towards the left, okay? You're going to get an electric force in this direction. Let me use a different color. Maybe I should use black, okay? You're going to get an electric force that is in this direction, okay? So if you consider that you want to move your charge from here to here, do you need to purposely apply a force to move it from here to here? You don't need to, right? Because you already have an existing electric force. It's different from the case above here. Because you want to move it towards the left, but there's already an electric force trying to oppose you, you have to purposely apply a force to move it against the electric force. You have to overcome the repulsive force. That's why we say what is done on the charge itself. But in the second case here, the electric force is already in the direction that you want the charge to move to. You don't need to purposely apply any force. You don't need to overcome any force. You just need to leave the charge as it is. The charge will actually just move by itself from infinity to some point in the electric field. Okay, so in our case here, we say that your positive test charge is actually being moved due to the attractive force. Your work is actually being done by the charge right now. No one is doing any work on the charge. The charge is actually doing the work by itself. So work is done by the charge. When it does work, when the charge itself does the work, its energy will decrease. If work is done by the charge, it loses electrical potential energy. Okay, so now you consider this. If you're moving from infinity to some point in the electric field, you're moving towards the left here, what you can say is work done by charge, therefore your EPE decreases. So now consider this, your EPE at infinity is 0. When you move towards the left, your EPE is supposed to decrease. So your EPE is decreasing from 0 at infinity. So whatever EPE value you have there should be negative, okay? So this is a case where your EPE can be negative. It can be positive or negative, all right? So if you want to find out the electric potential energy specifically at a point inside the electric field now, there is an equation that you will need to remember. That one is actually this one. W is equals to 1 over 4 pi epsilon naught Q over R. Okay, this is the definition, this is the equation for electric potential energy at a point. Okay, maybe I should just write it here. This is for EPE at a point. Okay, you want to find electric potential energy at any point, you will use this equation. Okay, so how do you know whether your electric potential energy will be positive or negative or not? It will depend on the sign of your charge. Okay, so this one I think I should write it here. Whether EPE is positive or negative depends on sign of the charges. For example, your test charge is always positive, right? So your main charge is positive, you will end up with positive potential energy. And if you consider again a different case where your test charge is positive, but your main charge is negative now, your electric potential energy will be negative, consistent with what you see above here. Okay, so whether your potential energy will be positive or negative, it depends on the sign of the charges itself. Okay, by default, it does not have any negative inside, unlike the gravitational field, unlike the gravitational potential energy equation. For gravitational potential energy equation, this one is very important to put in. Okay, but not for electric potential energy. It's different. Okay, so that one okay. Now, apart from electric potential energy, there's also something called electric potential V. Okay, so V here is a symbol for a physical quantity. All right, it is electric potential. So here, if you look at the definition of electric potential energy from before, we said that EPE is the work done to bring a charge from infinity to a point inside an electric field. This one is actually EPE. When you're talking about potential, potential is defined as the work done per unit positive charge to bring a small test charge from infinity to a point in the electric field. So the only difference here is that you have this term per unit positive charge. Okay. So if you look at your definition, work done to bring a small test charge from infinity to a point in the electric field is actually EPE, right? So when you're talking about per unit charge, this means that potential is actually just EPE over the charge itself, over the test charge itself. That's why here you can actually say that in terms of the equation, electric potential V would be EPE divided by the positive charge. So you will get 1 over 4 pi epsilon naught Q over R. If you sub this one here at the top into here, you will notice that the small q will cancel each other off. So giving you 1 over 4 pi epsilon naught Q over R. All right. So again, your electric potential can be positive or negative. It again will depend on your sign of your charge. Maybe I should write it here also. Whether EPE or potential is positive or negative depends on the sign of the charge. So in your case, potential is a bit more straightforward. It will really just depend on the sign of your main charge. If this one is positive, potential will be positive. If this one is negative, potential will be negative. Okay, that's how you evaluate your potential. And another thing I should probably mention to you here is this. Your potential has unit of volts, V. Okay, so it can get a bit confusing. The variable itself is V, the unit itself is also V. Okay, potential is measured in units of volts. All right, so from here, there's one thing I want to kind of mention too. Because you say that potential is actually EP over Q, I could also say that EPE is actually Q times your potential. Okay, that's why here is written as this. At a point in an electric field, the potential energy is related to its potential by W equals to QV. Because in the original equation for electric potential is EPE divided by Q, right? So EPE is therefore Q times V. Don't forget the potential here is V, okay? So EPE is actually Q times V. This is another different way in which you can find potential energy at a point, okay? All right, then one other thing I should kind of mention is this. Just give me a while to rub off everything. Another different equation that you use quite often in answering your questions is the change in EPE between 2 points. So I need to give you something like an example here. Okay, just give me a moment to rub everything off. Okay, now, if say for example, I have a main charge, big Q here, and there are 2 points in the electric field that I'm interested in. Let's just say point A and point B. Bear in mind that this is not at infinity. Infinity is probably somewhere here. Okay, so if you're talking about point A and B, the distance or point A from the main charge, let's call it RA, whereas the distance or point B from the main charge is, say, RB, okay? So right now, I'm interested to find out the potential at A as well as the potential at B individually, okay? So potential at A, you would rightly say it is 1 over 4 pi epsilon naught QA times the test charge divided by RA. And then when you're talking about potential energy at B, it will be 1 over 4 pi epsilon naught QB times Q over RB. Okay. So in your case here, if you have wanted to find the change in the change in EPE between these 2 points, say when you move from A to B, let me just find a suitable color. Okay, let's just say you're trying to move from A to B now in this direction. What is the change in your EPE? So one way of finding the change in EPE between these 2 points that you would normally can do, is to say change in EPE is actually the potential energy at B minus the potential energy at A. You take the difference between those two, okay? But there's also another way in which you can find electric potential energy between these 2 points, other than finding the potential energies at each point individually and then taking the difference. Another equation you can use is this one, okay? This one I can say as this. Just now I mentioned to you in the previous page that EPE is actually QB, isn't it? So this equation can actually be modified to become change in EPE equals to Q times delta V. Change in EPE between 2 points in an electric field is the charge times the difference in potential between the two same points. Okay, that's why here I can write this. Between 2 points in the electric field, your equation can be modified to allow change in potential energy or work done to be determined as this. Okay, right? So one thing that I should also mention before I go on to the next part is that electric potential energy and potential are actually scalars. There are no directions to consider, but nonetheless, they might have positive or negative values. All right. But just know that when you have a negative value, it's not an indication of direction, but rather an indication of the value. Okay. You will need to bear this in mind later on when you do some of the questions later. All right. So why do you need to know this? Is because of the next section. So let me just clear off everything here. Now, same thing as before. When you have two isolated charges, let's just say this one is positive isolated charge like this. And then you have another positive isolated charge like this. They are far away from each other so that they don't interact. If you bring them close to each other like this, what will happen is that the electric fields of both charges, specifically these two sides, will tend to overlap at the same place, same region. So the electric fields will combine and give you a new resultant electric field. Okay, so that is actually stated in this point here. Okay, so for the new resultant electric field that is between this region here, in the previous lesson, we talked about finding the resultant electric field strength as well as the resultant electric force there, right? So now we want to find out the resultant electric potential energy as well as the resultant potential at that point there where you have a new field set up, okay? So if you want to find out what is the value of the new resultant potential and potential energy, you again would need to use a positive test charge at the point that you're interested in, okay? So the resultant potential or potential energy at that point that you consider would again be due to the combined effects of the two individual spheres, okay? But here, you do not have any direction to consider because potential and potential energy are scalars. They still could be negative values, okay? Depending on the sign of the charges involved, all right? Although I say the potential energy and potentials do not have are scalars, there are no directions to consider, they could still be negative values in your analysis, mainly due to the sign of the charges that are involved. Okay, so let's look at the first example here, where you have both positive charges. You're interested in a point P somewhere between the two charges. Okay, so you need to consider the effects due to A and then effects due to B before adding them up. Okay, so now you consider the effects due to A alone. All right, I think it will be better for me just to start with electric potential. Okay, so if you want to find out the resultant electric potential at point P, the potential at point P due to A would just be VA. Okay, at this point, there's no direction there. Okay, now this VA here would be positive because you can see from the original equation before, potential is 1 over 4 pi epsilon naught Q over R. If this one is positive, this one will be positive. So your VA here, although it has no direction, you can actually evaluate whether it's going to have a positive or negative or not. This one will be positive. Okay. Then you consider the effects due to sphere B alone on the positive test charge. So it would have VB here, potential due to B here. And now if you're trying to evaluate whether the potential is going to be positive or negative, because it's positive, your potential would be positive too. Your main charge is positive, your potential would be positive too. Okay, so your VB would be positive too. So now VA, VB combined together will give you VP. VP is really just VA plus VB. There's no negative. All right. So then from there, if you expand it further, using this equation, you will get 1 over 4 pi epsilon naught Q over RA plus 1 over 4 pi epsilon naught QB over RB. Okay. Just be careful about what is your RA and your RB. Your RA is the distance between your main charge B and your point considered. Your RB is the distance between your main charge and the point considered. Okay. So you will do the same analysis for electric potential energy too. It's going to be the same thing. The only difference now is that you have the small q, the small positive test charge inside the equation. Potential energy just now I told you is W equals to 1 over 4 pi epsilon naught QQ over R, right? So the only thing different now is that you have a small positive test charge to consider. Okay, so in terms of finding out the expression for the resulting electric potential energy at the same point P, it's going to be the same analysis where you just say WA plus WB. WA would be positive, WB would still be positive. If you expand it using the equation here, this is what you get. Okay, so that is how you find the resulting electric potential energy as well as the resultant electric potential. Okay, now from there, if you look at these two equations, when you want to find out what is the graph, let's just say you want to plot a graph of potential versus distance x or potential energy versus distance x. Distance x is this, okay? I should mention this to you. Distance x is the distance measured from sphere A towards the right. This is distance x. It's actually indicated inside your diagram. If you want to find out the variation of your electric potential energy or electric potential with x, your graph shape generally must look like this. Okay, one thing that you can actually see from this original equation that you have here is this. Your value, number one, will never be negative because a positive value plus with a positive value will never be negative. And then because it's positive value plus positive value, you will also never be zero. And that's why here when you see that you draw your graph, this little minimum point here will never ever touch zero, neither will it ever go to the negative side. Okay. And then as for why the general graph shape is like that, it probably can be explained like this. Just let me write something here. if I tell you VP is equals to VA plus VB, and then after that, it is 1 over 4 pi epsilon naught QA over RA plus 1 over 4 pi epsilon naught QB over RB. You consider this, if V is 1 over 4 pi epsilon naught, if V is 1 over 4 pi epsilon naught Q over R, your potential is actually inversely proportional to your R. Okay, which means to say this. If R increase, potential drops. If R drops, your potential increase. So now you consider this. If, say for example, my distance x increases, what this means for me is that RA would increase so that VA drops. And then conversely, RB will drop, but VB would increase. So what this means is that your VB will start to become larger than your VA. Your VB will become larger than your VA. Okay, so this particular case here is actually being reflected by this part here. Okay, then if, say for example, your X was decreasing, your RA will be dropping, so your VA is increasing, but conversely, your RB would be increasing, but VB would be dropping. So in such a case, what will happen is that your VA becomes more than your VB. So this particular case here is actually being represented right over here. Okay, so the more you go towards one side of the sphere, the effect due to that sphere actually becomes bigger and bigger compared to the other, such that if you go to the sphere itself already, the effect due to that particular sphere is already the maximum, whereas the effect of the other sphere is minimum. Okay, that's why you get the graph shape that looks like this right now. Okay, so I hope that is clear. Okay, now from there, sometimes we may ask you to deduce certain things from the graph of your electric potential energy as well as your potential energy. So without talking so much about this, I just tell you the general trend that you should be able to see here. If you're going from here to here, your EPE is actually dropping because you see the value is dropping, right? So here I can say that my EPE is dropping, but according to conservation of energy, my kinetic energy should be increasing. Okay, so for this particular section, section 1 here, you could say that your EPE is decreasing, kinetic energy is increasing, so your charge is actually speeding up. Okay, but because you see that the change or the gradient of the line is decreasing at a decreasing rate. No, how would I say this? Okay, maybe I don't talk about the increasing rate, decreasing rate first. Okay, don't bother about that one first until I go through the question, then I'll explain this again. But for now, just consider this now. When you're going from here to here, your EPE is decreasing, so your KE should be increasing. Okay, but how does it actually increase, decrease? This one, I'll leave it for the past question later. Now, then after that, you look at the other part where you see this particular point. What can you say about your KE and PE? Your KE and EPE? Your EPE is actually increasing in value, so your KE is actually dropping. So for this section 2 here, you're actually slowing down, okay? Your EPE is increasing, KE should be decreasing, your charge is actually slowing down, okay? Then from there, there's one particular point of interest to you. This particular point here would be where you have max speed. Because you consider this, before this, you were speeding up. Then after that, you start to slow down. So the point where you change from speeding up to slowing down obviously would be where you have max speed. Okay, so that's how you would kind of look at the graph. All right, then after that I move on to the next analysis. Okay, now for the next analysis, it's still the same thing for two charges, but this time I change the sign of one of the charges. So in my case, let me just zoom this thing in closer. Right. So in your case, your charge A is positive, your charge B is negative. Again, I have a point P right in the middle of the two charges, and I'm interested to find out what is the resulting electric potential energy, the resulting electric potential. So I start off with electric potential first. So if you consider the effects due to sphere A alone, you will have potential VA here, but no direction to consider. Since your charge A is positive, your VA must be positive. Okay, then you consider the effects due to sphere B. Sphere B will cause a potential VB at this point here, but because it's negatively charged, your VB would be negative. Okay, so if you want to then find out what is the resulting electric potential at this point, it's just Vp equals to Va plus negative Vp. Okay, then if you expand it further, this is what you get. Okay, now if you repeat the analysis for the same question, same example here for electric potential energy, this is what you're going to get. All right, the analysis is exactly the same, where you first need to consider the potential energy at A as well as the potential energy at B. Potential energy at A, you find out is positive. Potential energy at B, you find out is negative. So you're going to get back something similar. Okay. But for the case where you now want to find out your electric potential energy or potential versus distance graph, your graph now looks like this. Okay. So it's kind of similar again to why the graph looks like this is kind of similar to what we did before. This one I probably have to write it very quickly. If you say that Vp is Va plus with negative Vb, this one will become 1 over 4 pi epsilon naught Qa over Ra plus 1 over 4 pi epsilon naught. I don't have space here. Let me just rewrite it on the left hand side. Vp is Va plus negative Vb. So this is 1 over 4 pi epsilon naught Qa over Ra minus 1 over 4 pi epsilon naught Qb over Rb. Okay, so same thing as before lah. If you say X increase, Ra drops, Ra increase, Va drops, but Rb decreases, Vb increases. So that now Vb is more than Va. But if say X decreases, Ra decreases, Va increase, but Rb increase, whereas Vb drops. So that now Va is going to be more than Vb. Okay. So if you look at this one right now, because your Vb is negative, all right, your Vb is negative, whereas your Va is positive. What this means is that when your X increases, your Vb is getting progressively larger than your Va. This one will become more and more negative. That's why you see this part here. Okay. And then after that, if you talk about your X decreasing, your Va would be progressively larger than your Vb. This means you will become more and more positive. That's why this one is represented over here. Okay. Do you go more towards the left? you will become more and more positive. If you go more towards the right, you will become more and more negative. That's why your graph looks like this right now. Okay, and not to mention, you will actually have one particular point where you have 0 resultant potential. This point here is where VA is exactly equal to VB. Okay, right? So that's how you get this graph shape. Now, if you consider the energy changes that are occurring in this particular graph, you will notice that from the start to the end here, your EPE is really just continuously decreasing, so that your KE is always just going to be continuously increasing too. So your charge is always speeding up from start to finish here. Just that they will be doing so at a decreasing rate and increasing rate, depending on how the gradient looks like. Okay, so this is for the analysis for unlike charges.